In a modern enterprise network, for every single human identity operating within the system, there are 80 non-human identities. These non-human identities, or NHIs, are the machine-level credentials that keep infrastructure running. They take the form of service accounts, API keys, which are unique strings used to authenticate applications, and bearer tokens. The security industry manages these credentials through a predictable lifecycle: discover the identity, contextualize its permissions, remediate immediate vulnerabilities, and monitor through ongoing governance. But this lifecycle contains a severe structural flaw. It relies entirely on shared secrets. These are plain text strings or passwords that must be stored and transmitted, making them highly susceptible to being stolen, leaked in public repositories, or simply forgotten on an active server. The sheer volume of these shared secrets forces enterprise security into a purely reactive posture. Security teams are perpetually hunting for leaked keys across thousands of code bases, often identifying breaches only after the credentials have been compromised. The identity and access management industry treats the explosion of non-human identities strictly as a detection and remediation problem. Governance platforms like StackGuard have built extensive tooling around this assumption. They operate by continuously scanning environments for leaked secrets and enforcing rapid token rotation to limit the lifespan of a compromised key. While rotating tokens more frequently limits the window of vulnerability, it does not address the core architectural failure. The flaw is the use of shared secrets in the first place. SG-Send operates on a different thesis: the migration to a zero-knowledge public key infrastructure, or PKI. PKI is a cryptographic system that uses mathematical key pairs rather than passwords to establish identity. In this model, shared secrets simply do not exist. True security at scale requires eliminating the shared secret at the architectural level, rather than building faster scanners to find those secrets after they leak. This architectural diagram shows the base layer of the zero-knowledge model. It begins with the SG-Send RSA key registry, which acts as the authoritative cryptographic inventory for the entire system. In this system, every identity, whether it belongs to a human user or a machine, is mathematically anchored to a cryptographic key at the exact moment it is created. A non-human identity is identified exclusively by its public key fingerprint. Because this fingerprint is inherently public and intended for distribution, there is no sensitive secret material available for an attacker to steal from the registry. This solves the pervasive problem of zombie identities that remain active in legacy networks. In traditional systems, outdated identities persist because revoking a shared secret that has been distributed across multiple microservices is highly complex and difficult to verify. The RSA key registry replaces that ambiguity with explicit revocation. Unpublishing a key from the registry is instantaneous, atomic, and mathematically verifiable by any connecting party. The necessary companion to this registry is the transparency log, which functions as an immutable, append-only chain of events. This log records every single key operation, creations, lookups, and revocations, producing a tamper-evident history of the entire network's identity lifecycle. By relying on the transparency log, security teams eliminate the need for unreliable heuristic log scraping, governing instead with definitive cryptographic evidence. Combining a centralized registry with an immutable log ensures machine identity is anchored to a verifiable public record. This split-screen diagram compares a standard micro-interaction between two services to show exactly how they prove their identities to one another. On the left is the legacy approach. A service transmits a bearer token across the network to gain access. A bearer token is a string of characters that grants access to whoever holds it, much like a physical hotel room key. The inherent risk here is transmission. The moment that token moves over the wire, it becomes vulnerable to network interception, logging errors, and unauthorized credential spillage. On the right is the proposed alternative: authentication by decryption. Instead of transmitting a secret, the requesting service must solve a mathematical challenge. The process works in reverse. The receiving service sends a locked challenge back to the requester. This challenge is encrypted specifically with the requesting service's public key. The requesting service proves its identity by successfully decrypting the challenge locally using its private key and returning the correct answer. The architectural result is definitive. At no point does a secret ever travel over the network. If no secret is transmitted, network interception yields nothing. This eliminates secret spillage from network traffic, closing the primary vector that scanners monitor. This network map illustrates the macro architecture of a modern enterprise. It is a sprawling ecosystem filled with thousands of microservices and active AI agents communicating constantly. Currently, these massive systems are governed using monolithic, overprivileged shared service accounts. If one service is compromised, the shared account grants the attacker lateral movement across the entire environment. SG Sens addresses this with the SG panel identity concept. This approach breaks down the monolithic service account into highly scoped, per-component PKI identities. Every single web component and microservice receives its own distinct cryptographic identity. These micro-identities are third-party verifiable because they are anchored directly to DNS records. DNS, or Domain Name System, is the Internet's standard directory, allowing external governance tools to publicly confirm an identity without relying on a central authority. This logic extends down to the data level through per-file PKI. Applying a cryptographic identity directly to an individual document or artifact creates an unbreakable, mathematically verifiable custody chain, which is critical for strict compliance environments. Applied to AI agents, this framework utilizes signed communications. By cryptographically signing messages, it eliminates the risk of one AI agent impersonating another across the network. Cryptographic identity allows networks to implement precise microsegmentation at scale. It delivers granular access control across millions of individual components without the corresponding growth in secret management overhead. The introduction of a zero-knowledge PKI architecture is an integration path for existing non-human identity governance platforms, not a replacement for them. There is a clear division of labor. SG Send provides the underlying cryptographic identity substrate, while platforms like StackGuard sit on top of that substrate to provide full lifecycle management and high-level policy enforcement. This shifts the mechanics of discovery. Instead of burning massive compute overhead continuously scanning repositories for leaked secrets, discovery becomes a lightweight, efficient query directly to the key registry. Auditing transforms in the exact same way. Governance platforms no longer need to scrape network logs using heuristics. They simply ingest the deterministic data output from the cryptographic transparency log. When machine identities self-register, when they self-describe, and when they self-revoke, governance platforms are freed from the reactive burden of detection, allowing them to focus entirely on enforcing security policies. The ultimate goal for enterprise infrastructure is to structurally reduce the attack surface of machine identities. SG Send has already proven this zero shared secret workflow in live production environments, operating across workspaces, encrypted vaults, and command line interfaces. We are looking at a choice between two distinct engineering paths: the outdated necessity of managing stolen secrets versus building an architecture where those secrets never exist to be stolen in the first place. Implementing authentication by decryption over a PKI registry is the definitive migration path away from legacy bearer tokens. By anchoring infrastructure to cryptographic provenance, the industry transitions non-human identity security from a cycle of reactive patching into a deterministic engineering discipline. The architectural shift from shared secrets to cryptographic substrates provides a verifiable path towards securing the modern machine-to-machine landscape.